If you look at machine learning and you just look at the trajectory, it's all a trajectory measured in terms of big data or the number, how many billions of parameters can your large language model handle. That's exactly the wrong direction from the point of view of the physicist. You should be looking for the least data, the smart data, the sparse data that you need in order to resolve your uncertainty.
Hello, everyone. My name is Stephen Parton, and you're listening to the Feedback Loop by Singularity. This week, my guest is Professor of Neuroscience at University College London, Karl Friston. Viewed by many as one of the world's most influential neuroscientists, Friston rose to prominence when he pioneered one of the key techniques that allows neuroscientists to analyze brain activity. And if that wasn't enough, he has since developed the free energy principle, which some see as monumental to the field, as Darwin's theory of evolution was for biology and genetics. It's this work on the free energy principle that will be the bulk of our conversation in this episode. And I want to warn you now that this is probably one of the most intellectually challenging conversations that we've ever had on this show. Therefore, in order to help you navigate this conversation, I just want to offer you a quick framing that may aid you in understanding the ideas that Professor Friston will be putting forth. In essence, Friston's work roughly states that entities that exist must track the information in the world around them, create an internal model of that information, and then use that model to navigate the world in a way that reduces the difference or the error between what they actually experience and what the model predicted. This concept may seem simple on the surface, but the actual science behind it is very detailed, very complex, and it actually holds immense implications for how we develop artificial intelligence and machine learning. So, if you're ready for this intellectual challenge, then take a moment to prepare yourself, and then when you're ready, come back, press play, and welcome to the Feedback Loop, Karl Friston. Well, before we get into anything too technological and technical, I think a good foundation for us to start on is to understand the free energy principle. Now, I know this is a often complex or complicated idea that you've talked about elsewhere that has a lot of details worth explaining, but I'm wondering if you could kind of start us off by just giving us a layman's overview, some very basic key points about the idea of the free energy principle.
My usual response to this question is, I think there are two roads to, a quick understanding. So the low road would be that taken by a neuroscientist or a psychologist, and the story starts probably with Plato and through Kant and Helmholtz and through some great psychology in the 20th century, ideas which were then taken up in machine learning, and now we see them in artificial intelligence research. And all this story is basically that we are prediction machines, that we, our brains at least, are in the game of trying to make sense of all the sensory data that our senses gather in terms of what could have caused that. They put it as simply as possible. The idea is that we don't extract information from sensory data or sensory input. What we do is a much more constructive act of perception. So it's a sort of inside-out generation of prediction. So we try to predict, if the world was like this on the outside of my sensory veil or my sensory blanket, what would I expect to see? And then I take what I'm actually seeing and subtract it from what I predicted I would see to form a prediction error, which measures the surprise that I have about my hypothesis or model or fantasy about what's going on out there beyond the sensorium. And we use that surprise or prediction error to adjust our hypotheses, our models, our fantasies, our internal representations in order to resolve that prediction error. Another way of looking at this is you're trying to find those explanations for your sensory data that are least surprising. So you're trying to minimize your surprise, prediction error being a measure of the surprise. So that's the low road. If you want the high road, even more briefly, if I can, the high road would be basically how can you describe self-organization through the lens of physics? That basically entails describing the principles, usually principles of least action of the kind you learned at school, that are apt to describe self-organization to non-equilibrium steady states. And you may be asking, where does the free energy come in? Well, this is a particular kind of free energy used by Richard Feynman, is trying to solve a very similar problem of evaluating the evidence or the probability of certain paths or trajectories. For him, there were little particles traveling through the ether. For us, it's basically the paths we take, the narratives we pursue in our life, in our active engagement with the world. But the maths is exactly the same. So this free energy is just a bound on or a proxy for either surprise or negative surprise, which is log evidence. And in machine learning, it would be known as an evidence lower bound or an elbow. So as we either maximize the elbow or minimize the negative free energy, then we are basically describing exactly the same process of making sense of the world by maximizing the evidence for our models of the world or minimizing our prediction errors. That's basically it.
So you can tell me if I'm wrong with this gross simplification, but would it be fair to say then that we have basically a thermodynamic and what I would say is maybe like an informational theory version of the free energy principle, where both basically say that you have a world of energy or information, and a system or entity that exists must find a way to model the information of the world around it and continually update that model in a way that will reduce the likelihood that its model is incorrect, that it will be surprised by something that it didn't model. Is that, in a very simplified manner, fair?
Yeah, absolutely. You've clearly read the papers. That's absolutely true. And you make an interesting point there. A thermodynamic reading of free energy is distinct from the kind of free energy that we were just talking about, which is much more information. It's all about beliefs about states of affairs in the world, cast as probability distributions, and of course, the same kind of mechanics you get in statistical mechanics applies to these probability distributions that are encoded in the way that we represent and think about the world. But probably even more interestingly, there is no real distinction at this level of mathematical description between energy and information. It's all the same thing, and which is important. Again, just thinking about the sort of issues of sustainability and the like. What that means is that in a free energy minimizing system, artifact, or person will not only make the most sense of the data at hand from the point of view of an information processing system or a statistician, but it will also do it in the most energy efficient way. So it will also minimize its thermodynamic free energy, which is, I think, an important way of reading the foundations of this kind of self-evidencing and sense-making. It's finding an account of the world, formally from the point of view of machine learning or a statistician, finding the right generative model that can provide or generate predictions that are as accurate as possible, but also minimally complex, minimally with a minimum degrees of freedom. I emphasizing that because that connects back directly to what we were talking about before in terms of the thermodynamic cost. So for any inference, for any belief update, for any data assimilation, there will be associated with providing an accurate account in order to minimize my surprise or my prediction error, there will be a complexity cost that attends that belief update, that information processing. And that complexity is, if you like, via things like Landauer's principle, the Jinsky equality, that's the thermodynamic cost. It costs energy, joules, to change your mind, literally. And that complexity is exactly the measure of how much you've changed your mind, which, I think has enormous implications for the direction of travel of, say, machine learning or artificial intelligence. One could argue that if you have to solve a problem by just injecting more data and more joules and more money and more energy into a solution, that's probably the wrong way to go.
Well, given all that, I mean, you alluded a lot to machine learning there and artificial intelligence. And what are some of the implications that this principle holds for the development of AI? What are some of the things you're finding that are really pertinent? Are we just throwing money and computation and power and energy at it, like you said, and foregoing kind of the parsimonious proclivity that the universe seems to be compelling us towards? Or are we finding ways to make these more efficient systems that are able to navigate this balance between accuracy and flexibility in in an efficient way?
You phrase that very nicely. I have to remember that.
Thank you.
Yeah, absolutely. I mean, this is an issue which is exercising a lot of colleagues, not just in academia, but sort of colleagues in industry and in people who aspire to provide the right kind of technology, information service, the right kind of tools that will enable that will enable a naturalization of belief sharing, of shared intelligence, a move from the age of information into the age of intelligence, and thinking very deeply about this. And I suspect very much along the lines that you are thinking about, and probably most of your viewers. So the implications of this way of thinking about message passing and belief updating and distributed intelligence, I think, are quite profound, and the way that we would deploy artificial intelligence and machine learning. So, I mean, you picked up on some of the key things. If you just look at this through the lens of, say, a theoretical biologist, and just think about what are good ecosystems. If you look at this through the lens of a neuroscientist or a neurobiologist and think, what are good brains? Then you come to exactly the same conclusion, that the goodness is in the sustainability. So that can be read in a number of different ways, and possibly I don't want to be adversarial, but certainly from the point of view of the physics, it speaks to a direction of travel which is exactly orthogonal to where machine learning is going. If you look at machine learning and you just look at the trajectory, it's all a trajectory measured in terms of big data, or the number, how many billions of parameters can your large language model handle. That's exactly the wrong direction from the point of view of the physicist. You should be looking for the least data, the smart data, the sparse data that you need in order to resolve your uncertainty. And furthermore, you should be doing it cheaply, you should be doing it on the edge and thermodynamically as efficiently as possible. So that would be one, if you like, important implication of committing to this, if you like, physics of intelligence and self-organization. The other big difference that sort of hits you in the face is the objective function. And I don't have your nuanced understanding of the singularity, but I certainly understand the paperclip paradox, for example. And that is actually disallowed under the free energy principle, because the whole point of the free energy principle is sustainability. And sustainability is defined operationally by the constraints that define that attracting set of states, that characteristic set of states that sort of characterize me or my family or my ecosystem or a world wide web. So what that means is that a good system, a well-engineered, functioning for survival, any ecosystem that's going to be here in 1 year, 10 years, and a century must be, if you like, suitably constrained in this kind of way. Does that make sense?
It does, but there's a little bit of I want to actually push back on a bit if I can, and specifically it's because I'm thinking as you're talking about that the constraints, the things with the paperclip model being kind of forbidden in this instance, and I'm thinking of Richard Dawkins and his idea of the selfish gene, but where he also introduces memetics, and that makes me think of language and culture and the agency that humans bring to the table, and the fact that we're crafting these AIs. And I guess my wonder or a question that is coming up for me when you're saying this is, does the introduction of language, does the step away from genetics and these kind of more purely physical systems into the realm of thought allow us to start creating maladaptive systems that kind of break those constraints? Are we actually able to, because we're crafting the models for the AI, because we're reshaping our environment as humans, it feels like we are able to break to actually build a world that doesn't match the model that we built over millennia, right? The human animal has built a model for maybe 600 million years total with the nervous system. And now we're building a completely different environment that is kind of maladaptive for that model. And I guess that's my long-winded way of saying, are we breaking those constraints? Are we breaking that chain by having some agency?
There are so many really interesting points that question raises. I think there is a danger. So in my head, I'm thinking, well, the free energy principle prescribes a utopia. If utopia is the naturalized way of any given sort of distributed system or ecosystem developing. But there's also a dystopia, and I think you're speaking to that. And I think that's perfectly right. The second thing that comes to mind is that you talked about evolution. So evolution, from my perspective, is just a free energy minimizing process. Very, very simply so.
Yeah.
Natural selection just is our way of reading nature doing Bayesian model selection. How do you do Bayesian model selection? The model, of course, being the phenotype. I am a hypothesis that evolution is using to test whether I'm a good fit to my environment. And I will be selected if I have a high marginal likelihood of existing in this environment. This is its Bayesian model selection, again, practically done by choosing those that optimize the free energy or the pathological free energy. So evolution and co-evolution and also cultural evolution, and I'm taking now sort of the Evo-Devo perspective. It's not the selfish gene. It's not. There is no yet single unit of selection. There are multiple time scales. There are multiple scales, and there are also multiple scales of phenotypes from my gene to my body. But also you brought in language, and of course language is just a facet of this kind of free energy minimizing process. It is a natural consequence. Interesting, I think, a reflection of something you introduced right at the beginning, which is this sort of this tendency to become more sophisticated and more complicated, paradoxically, as we minimize our free energy and become simpler and more efficient. I think that one has to ask, well, why? Why on earth do we get more and more sophisticated, yet at the same time, almost by definition, if you subscribe to the free energy principle, we're finding simpler and simpler ways of modeling our world. And I think it's because we live with other things like ourselves that are very complex. Just you being there and us having this conversation means that I have to spend more and more complexity cost in order to keep up to have an accurate model of you and all my conspecifics and all my colleagues and friends and family. So to come to the dystopian thing, how could you break that? I think you can break that. The way that you can break that, well, just think about how you can break evolution. When you think about the ways that you can break evolution, you think immediately about selection for selectability and experiments where you render the environment so quickly changing. I mean, you referred implicitly to sort of niche construction and the design environment, the fact we now create more of our environment than the environment does, by pure nature. So we're in the game now of thinking about the selection for selectability or evolvability being driven by environmental change. So we're now thinking about pressures on or potential disruption of this evolutionary steady state or non-equilibrium steady state that are due to things changing too quickly.
Mm-hmm.
And I think that is a real concern. Yeah, we are still evolving. Natural selection still works if we build artificial intelligences that make too many paperclips to our detriment. We're not going to buy those things. I heard a wonderful earlier on from smart cities that somebody at some point is going to build an office that will recognize that there's too much sunlight coming in, or there's not enough carbon dioxide on the inside, the outside, and we'll lock all the doors, trapping everybody inside. Now, of course, this would be a dystopian example of empowering artificial intelligence in a way that ostensibly is for our own good, but of course, treads on the toes of the other multiple constraints that really define goodness. But I think the point is, no one's going to buy that system if it does that sort of thing to you. So just the fiducial, the sort of the way the market economy is just part of this natural selection. So I think the route to that dystopia is it's certainly imaginable, but I can't really see it actually happening in any system, with one exception. And that's the exception is that if you just think about the sustainable individuation of multiple systems, artifacts, agents, people, communities, then you are compelled to think about what defines and individuates any one member of that ensemble. That individuation rests upon a sparsity of coupling. Technically, we usually talk about this in terms of something called a Markov blanket, a statistical, and that was actually at the heart of the free energy principle that sort of separates the inside of me from the outside. But the point here, I think, ways and routes to dystopia. If you degrade that Markov blanket, then that would be disastrous. From the point of view of a biologist, you're talking about something that decays or dissipates, dies, simply in virtue of the fact you've lost your boundary, you've lost the thing that sort of distinguishes yourself from the stochastic chaos out there. That boundary rests upon sparse coupling. And that's what I think is very fragile at the moment. This ability to actually separate, to induce conditional independences, to not be overwhelmed and overconnected. So I think in the current age, then we are in danger of destroying that sparsity, that delicate sparse structure. So it's, one example I often use, just to emphasize the importance of sparsity, the beauty of a sculpture inherits from what the stone that has been removed. It's what's not there that's important. In the same way, any ecosystem, any distributed system, any graph that works with functions on that graph has to be sparse. It has to have a sparse connectivity. And if we break that by over equipping people with the ability to communicate, I think we are in danger. So, I'm not politically very fluent, but I'm assuming that many aspects of globalization are in danger of destroying the sparsity that really underwrites our existence, in the sense that it allows us to be individuals relating in a sparse and smart way to other individuals. So I think that is a danger. So there's going to have to be some agile movement in and there has been some agile movement in the past few decades, but certainly in the next few decades, until we can get on top of what I've heard some people describe as a sort of not infant stage, but certainly adolescent stage, and getting used to the ability to communicate with anybody and share anybody. So I think that is a real challenge.
You have a amazing history, with brain imaging, and as we enter into this future study of the brain, it'd be really lovely to get kind of a little bit of awareness from you in terms of where you feel like the field is going, neuroscience specifically because of technology. Are there new imaging techniques that are coming down the line that are on the horizon, or things like brain-computer interfaces that you're particularly excited about with this relationship between technology and neuroscience?
There are certainly developments every sort of well, every year, but certainly usually every 5 to 10 years. So in my somewhat restricted world of non-invasive brain imaging, the big thing recently has been optically pumped magnetometers, which enable you to literally look at the fluctuations in message passing, the electrochemical signals in the head during active engagement with the world. So there's like a wearable magnetoencephalography. That's quite exciting, and that's becoming not mainstream, but certainly standard. With at least one of these centres per nation at the moment. So that's giving us a very sort of fine grained, certainly in terms of time, understanding of the message passing, and sort of the World Wide Web inside your head, and interestingly, all those structural attributes that we were just talking about in terms of sparse connections and hierarchies. If you think about, just think about sort of deep learning. Why do people call it deep? Well, it's hierarchical depth. So that hierarchical structure, where does that come from? Well, it's the missing connections again. It's that sparsity of connections that you don't get connections that transcend multiple levels. And that is, if you like, one of the cardinal things, certainly for me, of interest in trying to understand the computational and the functional anatomy of my own brain, or brains of our experimental subjects.
Is this new technology, sorry to interrupt, but is this new technology more portable, or does it work well with movement? Because one of the big issues, obviously, with imaging is you have to lay in an fMRI machine and you can't move at all, and it really limits our ability to conduct interactive, really like lifelike examples. But is this solving that?
Yeah, in principle, absolutely. It's still very early days. There's still a lot of development work and validation work, but that's exactly right. So, the dream is that you could deploy this kind of technology where it matters in terms of movement disorders or children with epilepsy, or in ambulatory studies. You could use it in sports medicine. So just practically speaking, it is like a wearable MEG or magnetoencephalography, and you have a big room that you. And usually, it's my colleagues, the Wellcome Centre for Human Neuroimaging, people like Eleanor Maguire and her colleagues. They built this wonderful world inside this enormous magnetically shielded room, with sort of virtual realities where you can walk around whole towns. This one's called Filbury. And have conversation with people and sort of move around. So the potential is great. And as you rightly point out, ultimately the idea would be to use this in a translational setting, in a clinical setting, and look at things like Parkinson's disease and epilepsies and neurodegenerative disorders, where that entails some kind of abnormal behavior or motor function, so that you can do it almost in the field. It's not quite going to be bedside technology, but it's certainly you could bring a bed into these rooms and so you use this technology. That's just one example. You mentioned sort of brain computer interfacing and the like. I'm less enthusiastic about that. But certainly a sort of more conceptual level. So, the increasing dialogue between people in artificial intelligence research and machine learning and neuroscience, I think, is exactly the right direction of travel. So I think that dialogue is, for me personally, very exciting, but also I think can be more center stage in discussing these kinds of societally important issues.
Are you less enthusiastic about brain computer interfaces because it's just not something of interest to you, or because it's something that you don't have as much information on, or do you feel that it is potentially overhyped? Does it have as much potential as people like Elon Musk and others are making it out to be? Do you think we'll see real brain computer interfaces that go beyond limited medical use in the near term, and is it really feasible?
Um, yeah, my attitude to this is based upon watching the development of this field over several decades, and lots of my brilliant colleagues have made great advances, but we're still, we're talking about sort of bits per. I was going to say minute. That's very unfair, but it's only bits per second. So, where it matters in terms of enabling people to walk again after spinal cord injury, or being able to assess locked-in syndromes, or minimally conscious patients and the like. I don't think it's going to go beyond sensory substitution and just having a direct sort of wiring into the brain. I just don't think that that's ever going to happen for quite principled reasons. But they're not, if you like, pessimistic reasons. I think we've actually all really enjoyed brain computer interfacing in a really profound way for several years. It's just hasn't been recognized as such. I mean, you could argue, people like Andy Clark would certainly argue, that the iPhone is such a wonderful piece of BCI. Well, now, literally, I'm sure that my children's memory circuits and memories are just not the same kind of my memory circuits, because they don't need it. All their memories on their iPhone. And I think that the kind of issues that you have to deal with speak to this. That there's been this sort of this downloading, this sort of extended cognition available to us, that has been facilitated by a certain kind of brain computer interfacing, but it's just not where you plug wires into the cortex, which it's a fun thing to think about, but I'm not sure it's terribly necessary. And there are other ways of using computers of a mechanical or a silicon sort to augment our lived world, and to share in the shared intelligence that we're all aspiring to in a safe and sustainable way.
Without getting lost and losing yourself. As we wrap up here, I just want to kind of get a big picture takeaway from you, get maybe some closing thoughts. As you look forward, is there anything that you would love to see people talking more about? Something maybe that you're concerned about a direction we're going, or maybe something that you would hope more people would pay attention to, something maybe that's going under the radar that deserves more attention?
Yeah, well, yes. I mean, it's a very, I was going to say selfish, but well, it is selfish at one level from an academic point of view. But I think pertinent in relation to the things that we've been talking about in terms of direction of travel in the way that we use our resources and energy in making the world a more sustainable place, and one that is more apt for us to be integrated within our self-made ecosystems. And that's just, again, committing to this biomimetic, naturalizing way of thinking about the self-organizing systems and what that brings to the table. And we've talked about that, and I'll just try and summarize that with one cardinal feature of the kind of behavior that we should be aspiring to facilitate or indeed engineer in our intelligent artifacts and agents, which is exactly the exploratory thing that we were talking about before, curiosity. So what we have to do, I think, is take much more seriously curiosity as a quintessential feature of just being as part of an ecosystem.